I work at JP Morgan, where I spend a lot of time making very complicated code much easier, while the rest of my team does the opposite, which is not ideal, but that's what I do for a living. And I'm here because I want to talk to you about data type modeling, because I find that when you're trying to solve problems, data type modeling is the key part. Once you have got that right, the rest of the problem tends to be very easy to solve. Oh, geez. Oh, that's not actually me. So I hope that's not going to keep happening, otherwise it's going to be an awkward presentation. Let's hope. Right, okay. So where was I before that turned off? Data type modeling, right. So I want to talk to you about data type modeling because, where was I? Blah, 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 hard problem, there we go. And through the course of my career, I've done a lot of data type modeling, and I have come to the conclusion that you could do it in either of two ways. You could either do it with algebraic data types, or you could get it wrong. And I have done it wrong quite a lot. So what we're going to do today is going to go through all of the ways I've done it wrong, the entertaining, interesting ways I've done it wrong, and try and fix those. And hopefully by the end of the talk, I'll have convinced you that algebraic data types have all the properties you want of a good data type that allows you to write software with trust and confidence that it's actually going to work. Now, before we get into the actual talk, there's a little bit of a backstory here. Because a few years ago, before I started working on that talk, I was having lunch with my family, and I was telling my wife how I had gotten some bad feedback on a previous talk about how my examples tended to be a bit dry, a bit boring, not very entertaining, and didn't do my talks any favor. And my son told me, well, don't worry, Dad, for your next talk, I'll pick the example. So given that my son is 5 years old and half Japanese, we're going to be talking about Gundams today. Now, don't get too excited. I don't actually know much about Gundams. I tried to research it a little bit. I got to the point where apparently sometimes they grow wings, and you have to call them Gundam wings. And I thought that sucked a little bit, so I stopped researching about that. So for the rest of the presentation, as we all know, Gundams are giant robots remotely controlled by Super Famicom gamepads. Anybody that knows anything about Gundams knows that, right? Yep. So that's what we're going to be doing today. And where we can send a finite known amount of commands to a Gundam to get them to work. So the first one is going to be to face north. And when that happens, the Gundam is going to obviously face north. And we have all the cardinal points here. We can face west to get him to face west, face south, and face east. And then you can get a Gundam to start, which is going to cause it to start walking in whatever direction it was facing, and stop, which is going to cause it to stop and keep facing whatever direction it was facing. So those are all the legal commands you can send to a Gundam. You can send lots of other commands, though, such as triple backflip, which is not actually supported. So the Gundam receiving that is going to be a little confused, is going to hesitate. And we all know what happens to a Gundam when it hesitates on the field of battle, don't we? That is known as an undesirable outcome, which we're going to try to avoid for the rest of the presentation. So the entire point is we have something that allows us to avoid that. The Super Famicom gamepad is what we're using to send commands to the Gundam, and we control that. We run code in that. So if we manage to make it so that it's impossible to express an illegal command, and we cannot send an illegal command to the Gundam, then we're going to be home free. We're not going to blow too many Gundams up. So the entire point is going to do something like that. If somebody sends us a command like face of -35, which makes no sense, the gamepad should be able to spot that and prevent the Gundam from blowing up. So that's what we'll be doing here. And the first thing we'll be doing is try to represent direction. So you've seen that we have the command face, which takes one of the cardinal points. How do we represent the cardinal points in a way that prevents Gundams from blowing up? So back when I was studying computer sciences quite a while ago, I was told this is the best way of encoding enumerations is to use magic values. So you open up a namespace called direction, and you stick magic values in there. So say 1, 2, 3, 4. Don't care which values, they just have to be distinct. And that back then, we're talking about 25 years ago, that was state of the art. So that sort of works. And then the first thing you do once you have these values is to write stuff that works with this value. And I usually like to go with a pretty printer. The first thing I usually write is something that allows us to represent a value in a way that's friendly to human readers. So something like that. Label which takes a direction, currently encoded as an int, and prints it. So I'm going to implement that as a pattern match. You could do that with a nested if and else statements. It's basically the same thing here. And what you do is for every single one of these, you pick up a label and just return that, right? So that works. That sounds that sounds reasonable. What do you think happens when we run that though, right? Face of minus 35. Minus 35 is an int. Label takes an int, so the compiler is going to accept that. However, we do not handle that scenario, so we get a runtime explosion, which, as we said, is exactly what we're trying to avoid. We don't want that to be happening. So what we have for the moment is not a good enough representation because it allows us to represent illegal states, completely nonsensical states. So what we're going to do instead, well, the next step I was taught to represent that was to use type aliases. So we'd say, right, well, we're going to create a type called direction, and we're going to say, well, that's equivalent to an int. That allows us to make our typing instructions a little bit more precise here. North, east, south, and west are actually of type direction. And label now takes direction. So for the human readers, that's a lot better, right? As a human, I know that label doesn't take any int, just a subset of ints that map to directions. As a human person, I'm less likely to make mistakes because I understand more what's going on in there. For the compiler, though, there's no difference. Minus 35 is still a direction, which maps to an int, so this is still accepted, and results in the Gundam blowing up. So still not very good, still not what we desired. And then once we get to that point, usually a few years happen and somebody mentions, well, enumerations might be what you're looking for. So we can try enumeration. Scala has built-in support for enumerations, which goes something like this. You remove all we've done so far, keep the namespace, have it extend enumeration, and then you do, I'm not actually sure how that works, because this is a bit of a spoiler, but Scala's enumerations absolutely suck. Never use them if you can avoid it. So I didn't invest much time in understanding that. Just this works. This declares 4 values, north, east, south, and west, which are of type direction. Well, actually of type direction dot value, which I think is a bit weird. I would prefer if it was just direction. But direction dot value, I mean, it's uncomfortable, but if this is what it takes to make sure Gundams don't blow up, we can live a little bit discomfort. That suddenly makes this a type error, because we're passing an int where direction dot value was expected, which is nice. We seem to have made progress. We can't send illegal values any longer. However, now I don't know about you, but when I have a bug in my code, when I have to debug, I'm sure lots of you are using debuggers. I have stopped doing that quite a while ago because it just doesn't work any longer. And you have to hook them to stuff that runs somewhere. Just so much work. So I use print line debugging. I just comment things out and print stuff. And so let's say I commented that out during one of my debugging sessions, and I forgot to uncomment it later. What do you think happens here? Well, direction.west is a valid direction.value. My pattern match does not handle that, though, so we get a runtime explosion. And this is exactly why you should never use Scala's enumeration, because this happens. They disable a behavior of the compiler, which is called pattern match exhaustivity checking, which we would really like to counter. Now, I'm going to explain what pattern match exhaustivity checking is in a minute, but that doesn't work because we still manage to somehow write code that blows Gundams up, which we really want to avoid if we can. So what's the next step? Scala's enumeration, Scala's built-in enumeration suck. What, as Scala developers, do we do when we find something like that? Obviously, we reinvent the wheel, right? That's what we do. When something built-in doesn't work, we rebuild it from scratch because it's fun. So we're going to write enumeration by hand. We're going to say there's some abstract type called direction. And in the direction namespace, I'm going to create values of that type, right? And those are all the values of type direction: north, south, east, and west. Now, having done that, I can get back to label, and now it takes direction, which is nicer. That's the preferred direction to direction of value. So at least that's some progress here. But of course, when we send direction.west, still fails to catch the error because pattern match exhaustivity checking is still disabled. Now, a bit about pattern match exhaustivity checking. This is what the compiler should be able to, this is a mechanism the compiler uses to tell you when your pattern matches are incomplete, when you have failed to handle all possible cases. And the way the Scala compiler handles that is a bit weird. Now we have somebody from the Scala Center here, so he might be able to explain. Oh, he woke up. Hello, James. The compiler will only try to check exhaustivity if it can for sure prove that it is not exhaustive. So it could check for exhaustivity when it knows it's exhaustive or when it knows it's not, and just not do it when it can't prove one way or the other. But here, the compiler cannot know whether all your types are handled because we're working on the JVM. It's an open word kind of thing, right? We could have a library that depends on our library and declares new subtypes of direction. So it's impossible for the compiler to guarantee that it knows all of the values of type direction because they might not all exist at compile time. Some of them might be declared later and brought up at runtime. Okay, so the compiler can't check for exhaustivity. However, the compiler does know that direction.west is a value that exists and that we're not handling. And for some reason that I don't quite understand, but Jamie, the Scala team has decided, well, we're not going to handle that. When that happens, we're just not even going to check for it, which is problematic. However, we can fix that. We can take our type direction and say, well, it's going to be sealed. Now, what a sealed type is we're saying all of the values, the subtypes of direction are going to be declared in that file. It is illegal to declare any other subtype of direction anywhere in the code. So with that, the compiler knows for a fact that all the possible values of type direction are north, east, south, and west. And since it knows exhaustively all the possible values, it will actually fail to compile here because it knows that we have not handled the west scenario. Right, so quick break. What have we learned so far? What we've learned is that enumerations make nonsensical values impossible to represent, which is quite great. We can't blow GADTs up that way. And it also forces us to handle all necessary cases when you write an interpreter, which is also really good. Of course, this is only true if you're not doing Scala enumerations, so don't do that. Just write them by hand if you can. Before I carry on, when you see one of these slides, it's a good time. I mean, this is an informal setting, right? There's not many of us. It's a little bit more familiar. So if you have questions, feel absolutely free. At these slides where it says key takeaways on top, interrupt me and ask the questions because I'm about to move into something more complicated. So if you haven't gotten what we've done so far, then the rest is going to be harder. No question? Yeah.
How does scala-italy enums fit in the picture?
In about 50, 60 slides.
Okay.
So enums in Scala-free there's a debate on whether or not they're well named. I would argue that they're not, but who cares? And they're not actually enumerations, they're algebraic data types, which I'm going to define later, but I don't have all the bits that I need to define algebraic data types at the moment. So we've defined enumerations. Now, we have defined direction. We still need to define the command type, right? And usually, again, when I was taught initially when I started doing computer sciences was, well, you're going to do that with a struct, a record, or in Scala, that's called a case class. What you're going to do is going to be the association of an order being the string face, start, or stop, and an optional direction, because well, if you have face, you need to have a direction, and if you have start, for example, you can't have direction, so you don't always need to have one, so you make it optional, right? So that's one way of representing it. I hope it's very clear for everybody that it's wrong in all kinds of ways, but that's where we start. Now, what do you think when I run that? Again, with a triple backflip, we know that doesn't work, and that's going to cause the GADT to blow up. But we know the solution to that, right? The commands that we can send are start, stop, and face. It's a finite set of values. We know how to encode that. We've seen that just a few slides before. It's an enumeration. So let's make order into an enumeration. Filtrate, so that we have pattern match exhaustivity checking. And in the order namespace, we declare all possible values, right? Okay, so we have our enumeration, and this becomes a little bit clearer. And this is now a type error, which is what we wanted. It is now impossible to send an illegal order. However, if we fix that, well, that's a bit of a problem, isn't it? We're saying start south, which makes no sense. I mean, it might make sense to you as a human, but that's not part of the semantic of what the GADT is supposed to accept. So again, start south, being nonsensical, cause the GADT to blow up. And we don't want to be able to encode that. And the problem is, with our model, it is possible to express start and stop with a direction, which makes no sense, and face without a direction, which makes no sense either. And the entire point of what we're doing is to make illegal state impossible to represent. Clearly, this is not achieving it. So the thing is here, face must have a direction, right? Let's encode that in the type. Let's just say that it takes a direction. And start and stop cannot take a direction, so we just don't give a direction field. And this looks about right, doesn't it? It's actually so right that this is not order any longer, which is a name I didn't like anyway. It's actually the command type that we wanted to write. This command type now has face with a direction all the time, start and stop without a direction. It's exactly what we wanted. And now this doesn't make any sense any longer to the compiler. It's going to reject it. If we want to say start, we have to write the corresponding command, which is going to work and cause the Gundam to start working. So pretty good. What have we learned? We've learned that enumerations are everywhere. We had a problem. The very first thing we reached for was enumeration, and that solved part of a problem. They're not quite enough. We had to tweak direction to be like an enumeration, but not quite an enumeration. But something like an enumeration, very similar to, but not exactly, has gotten us our solution. So we are getting closer and closer to the definition I want, to all the pieces I need to define what an algebraic data type is. There's just one more thing I need to explain first, but before I go to that last bit, any questions so far? Or can I carry on? All right. Now, we're doing functional programming. The essence of functional programming is composition. You take a hard problem, you split it into very small solutions that you compose together. We're going to want to compose commands again. Because if you, well, at the moment we can do that. What I'd like to do is that. Send all of these commands and have the Gundam run through them one after the other. And I want this sequence of commands to be a single command, so that I have atomic commands that I compose to create molecular commands, more and more complex, and I can compose all these huge molecules and send very complicated set of instructions, but that are, to me as a user, just a command. And the answer to the question is in the question itself, isn't it? I just said I want the composition of commands to be a command. So you just take the command type and say, I want a new variant here. I want a new branch in command. I want to be able to have something. I'm going to call it chain. Because when you have multiple commands and so you chain them together. I didn't realize there was a pun here, chain of command. This wasn't intended, but now that I find it, I don't mind, so let's go with that. This was fully intended as a chain of command. So a chain of command is composed of the first command and then the one you execute later. That simple, right? And now we have composable commands, which is quite nice up until the moment where you try to write one, because then you get that. And that is nasty, right? If you kind of squint and tilt your head a little bit, you can see that I'm saying face east, start, stop, and then face west, start, stop. This is not pleasant to read, and you only had to read it. I had to write it. I don't want to do that ever again. So what we're going to do is what every Scala developer loves doing. We're going to write a DSL. Oh, so what I'm doing is I'm creating a new command, a new operator. Given a command, I can squiggly arrow into another command to get the composition. Right? So when you do a DSL like that, it's usually good practice to also create smaller terse aliases for the terms of the vocabulary. So here, start, stop, and face, aliases for these larger things, and similar for the directions. And having done that, I can now write this command, move, which given a direction, faces that direction, starts and stop. And with that thing, I can now rewrite, remember that huge block of code from before? Now we have that, move east, squiggly arrow into move west. And that all works, right? That's going to cause the Gundam to face east, start, stop, and then face west, start, stop. So what we've learned here is we have completed our data structure by using three things. First, records, case classes, such as chain and face. Enumerated types, such as command and direction. And also we have had to make our data type recursive, because command is expressed in terms of itself. Chain is a command that takes command. So you have a command that's defined in terms of command. It's recursive. And that is everything I needed to start giving you a proper definition of algebraic data types. But before I do that, everything clear so far? No question? OK. So an algebraic data type. What we've written so far, command is an algebraic data type. Now let's look at it. Command is known as a sum type. A sum type is a face or a start or a stop or a chain, right? Here. So a sum type is something that can be thought of as an or between type, like we've done here, face or start or stop or chain. It's also a discriminated union. And I realize I don't have yet given you enough information to understand what discriminated means here. I haven't earned the right to use that term yet. So let me explain what discriminated union means here. In order to do that, I need to show you what an undiscriminated union is. So fair warning, if any of you have done C in the past, this is going to trigger your post-traumatic stress disorder a bit. For the rest of you, welcome to hell. This is how we did union types back in the C days. You said, well, this is an int or a string. And we either have an int or we have a string. Important thing, though, we don't know which one. We know we have one or the other. We have no idea which one. And so the way to work around that, because when you try to write print union, say, where you take an int or a string, you couldn't write that, could you? Because you didn't know which one you had. It could be one or the other. And if you got it wrong, well, this was C, right? So you interpret an address as an actual integer that you had no idea what's going to happen, probably something nasty. So this was an absolute nightmare. And the way to work around that was to create what we'd call the type tag, which tells us whether we have an int or a string. That's an actual enumeration, which can be a value string or int, and that tells us which one we have. So then you edit into string, and you say, well, it's also got a type tag, which I'm going to call a discriminator. Discriminator, undiscriminated, should ring a bell. And it's not a union any longer, because we are associating two values, a type tag and then the int or the string, so it's going to be called a struct. And this thing, we don't want an int and a string, we want an int or a string, so it's got to move back into a union. Right, so now, int or string is either an int or a string. We don't know which, but then we have the type tag to tell us which one we actually have. And once we've done that, if we go back to print, we have to fix the type signature because C is weird. And the code all but writes itself, right? If the discriminator is telling us we have an int, then we treat it as an int, otherwise we treat it as a string. And all this work we had to do manually, all this tracking of what we actually have, all this updating of discriminator that we have to do. And if you've done any of that, you know that we do it wrong. We always, at some point, fail to update it and then crash something. Well, that's what an undiscriminated union type is. We have manually added a discriminator to make it a discriminated union type, right? So that is what a sum type does for us under the hood. It keeps track of which one we have, so we don't have to, and we always know exactly which one we have, which is why we can use pattern matches and get the value we wanted. So a sum type is a discriminated union of values and can be thought of as an or between type. Direction is a sum type. So an ADT is a sum type plus stuff, right? It's clearly not finished as a definition. We also have command. If you look at chain is the association of two things. It's the association of two commands, right? The first command and the second command. So a sum type can also be that bit, the end. That's known as a product type. Product type is an aggregation of values and can be thought of as an end on types, right? So we've seen that command is a sum type, and some of its branches or variants or constructors, depending on how you want to call them, are product types. So an ADT is a sum type of product types plus something. The last bit that we need is command is defined in terms of command. The fact that command appears both on the left-hand side and the right-hand side of that type description makes it a recursive type. Command is defined in terms of itself, so it is recursive, and that is the last bit we needed. An ADT is a potentially recursive sum type of product types. And that is the definition of an algebraic data type, which has all the properties that we wanted. These properties are so good, so important to writing correct software, that scala-free now has a special syntax for it. If you take that whole thing, which is a lot, right? There's a lot of boilerplate, lots of code that we have to write. Well, scala-free allows us to get rid of that and just say enum. And then, well, if we're in an enum, we don't need these bits, and we don't actually need the type description either, because it's got to be a command. So get some things that's a little bit more palatable, right? This is understandable. This makes more sense. There's just one question. Is that actually an enum? An enumeration, for most people, is a finite set of values. This is not it. It's recursive, so by definition, it's not finite. It can be any length. So enum is a questionable choice. I think it was chosen because Rust does it that way. Okay, and so other languages do it that way, so we decided to do it that way. I think there was hundreds and hundreds of posts on the thread about that, and in the end, we just said, well, fuck that. We're just going to call it enum, and let's stop wasting time. It is, unfortunately, I have had people misunderstand what an enum was because of the keyword and tell, well, that's an enumeration. No, that is not what an enumeration is. It's at best an enumerated type, which is slightly different, but anyway, scala-free. So what have we learned? We've learned that algebraic data types are sum types of product types that can be recursive. And that is most of what I wanted to show you today. Now, we still have plenty of time, I hope, because I'm about halfway through. but from now, if we're running on time, you can stop me at any point. One thing we can go into more details, which is, well, it's a little bit embarrassing because it's going to force me to admit that I've been lying to you this whole time. I've said that we can compose any two commands. It's completely untrue. Because if you send start and stop, for example, well, the first start command is going to call the Gundam to start, and the second one, well, he's already started, right? What do we want him to do? He's going to be confused. Bad things happen to confuse Gundams. Similarly, stop and stop. He's already stopped, right? So what do we want him to do there? Again, confuse Gundam. And the worst of all, start and phase, right? So he's going to start, and then we're going to try to get him to change direction while walking. Nothing good's going to happen there. So we are going to want to fix that. We are going to want to make it so that it's impossible to compose two commands that make no sense. And we would like that to be expressed at the type level so that a compiler can find an error. And again, the answer to the question is already kind of in the question. We want that to happen at the type level, right? So we're going to need types. I'm going to create idle and moving, which represent the state of a Gundam. A Gundam is either idle or moving, right? And I've made this final abstract to make it clear that these are types only. It's impossible to create values of these types. They're just here as tool for the compiler and will have no existence at runtime. And we're going to use those to modify command, to make it polymorphic. It now has two states, two type parameters, before and after. The state the Gundam had before the command can be executed, and the state it will have once it's finished. So to make that concrete, phase is going to be a command of idle, because a Gundam must be idle before it changes direction, and it will be idle once it's done. Start, well, we have to be idle before we start, and once we have started, we are moving. Stop is the opposite. And change is a bit more complicated. That's where the magic comes in. So the first command is going to be a command of A to B. We don't know which A and which B. And the second command is going to be a command from B to C. And this is the important bit, right? The first command must end where the second command starts, so that we compose stuff that makes sense. They have to commute, I suppose. I don't know, not sure. They just have to work. And that's going to yield a command from A to C, because we're going to first run the command A, which starts on A, going to go to B, then run the second command, start from B, go to C, so we get a command from A to C. And of course, we need to declare all these type parameters. Now, we're going to have to rework our DSL a little bit by adding types. So our first command is going to be from A to B, which we need to declare. Second command is going to be from B to C, which we need to declare. And we get a command from A to C. And that's it, just fixing the types. And now, it's impossible to run that. The compiler is going to reject it, because we were going from idle to moving, and it was expecting something from moving to something, which is not what we have. We can't do stop and stop either, nor can we do start and phase. But of course, if we have something sensical, like phase is and start and stop, that all works. Sorry, that all works because all of these transitions are legal. So we have achieved safe state transition, which is nice. We have achieved something a little bit more powerful as well, which can be quite useful. We have, well, okay. Let's say that for whatever reason, this is not super useful, but I wanted to write a pretty printer just for commands that start from the moving state. Not sure why you want to do that. Would you want to do that? I just needed an example, so I came up with that. My son wasn't here to help me with that example. And in that case, well, command.stop starts in moving, so that's legal. Command and chain could start in moving, not necessarily always, but if it was, for example, the chain of stop and start, then it will start in moving. So we have to handle these two scenarios. And if we try to run command.start, which was not handled by a pattern match, well, the compiler is going to reject it because it's the wrong type. So we can't pass illegal values to our interpreters. Illegal states are still impossible to represent and to handle, which is nice. And also, if I were to do my usual thing of commenting things out to debug and forgetting to uncomment, well, the compiler would complain because our match is non-exhaustive. So we have to handle every possible scenario. But if I were to uncomment that, and for whatever reason add command.start to the pattern match, the compiler would tell us, well, yeah, that's not actually something that you have to handle because it's impossible to have that. So the compiler now tells us, You have to handle all scenarios, but only the ones that are needed. It will force us to do all the work that's needed, but no more than that, which is nice, right? And so again, quick break, what we've learned, we have used type constraint on type members to make a legal state transition impossible to represent. Nice. Guarantee that our code handles all necessary cases. We can't have unexpected exceptions because we have forgotten to handle a whole branch of our program, which is nice as well. And finally, that our code only handles necessary cases, which if you're lazy like me, not doing work that you don't need to do is something that's quite nice. So all these properties are really nice, and they make for something that's called a generalized algebraic data type, which is a really poor name for these things. I don't know what's generalized about them. Guillaume, actually, if you could get him to send me, he told me he would send me an article about generalized algebraic data types. I've been waiting for 3 years, so. He's been writing it for 3 years now, so. So I'm not sure where the generalized algebraic data type comes from. It's just, I suppose when you get something that's a little bit more powerful than something that already existed, you just stick generalized and say, yeah, that's generalized, and that's better. I think it just means better, really. So better algebraic data types. Come again? Oh, yes, right. Right, so how do we define a generalized algebraic data type? Well, command, as we've seen, is a sum type, right? Command has these branches, these variants. So a generalized algebraic data type is a sum type, plus bits. Now I'm going to need to define what a witness type is. Before, for example, is a witness type. It's an instruction at the type level. It's a type that gives us an important property of whatever we're working with. So is after, and the property is what state do I need to be in, or what state will I be in when I'm done. That's a witness type. It describes properties of a sum type's variants at the type level, right, before and after. And a GADT is a sum type with one or more witness types. We had 2 here, before and after. We could have just the one, or we could have any number. I have a friend who wrote something very complicated. It's supposed to represent narrative structures as a monad, and it had 18 witness types, but my friend is a little bit insane. Right, so that's part of the definition of a GADT. And the last bit is this, type equality. So by having a generalized algebraic data type and having that supported by the compiler is able to reason equationally about types. Here, it knows that we're looking for a before parameter that has to be equal to moving. So it knows that command.chain must be handled because it's going to run through all the possible combinations of command.chain, and it's going to see that there's at least one where the first parameter is moving. It's a chain of start and stop. So having done that, the compiler knows that we must handle chain by reasoning equationally through types. Similarly here, it's going to see that start has a before parameter of idle, which is not equal to moving. That doesn't type check, and it's going to reject that. So there's a lot more to type equality than I've done here. We could talk about injectivity of type equality and stuff like that, but let's keep things simple. That is what type equality is. It's information available to the compiler about each witness type, and that allows us to refine pattern matches. And that gives us a full definition of one possible full definition of a GADT is a sum type with one or more witness types, each equipped with type equality, which is a very complicated definition. So what we've learned is that a GADT is that thing. I don't think anybody's going to remember that. I don't. So really a GADT is a sum type with interesting properties for pattern matching. That's a good enough definition. So at this point, I can either be told to shut up and stop, or I can start talking about why they're called algebraic data types. Nobody's stopping me, so I'm going to keep talking.
Go on.
Okay. So I've been saying algebraic data type from this whole presentation, and I've not justified that term. Why are we talking about algebraic data type? Well, in order to explain that, first I'm going to have to explain what the cardinality of a type is. It is the number of values that a type has. So for example, nothing, the type nothing. We know the type nothing, it's in Scala. How many values does it have? None, right? No value, it's the empty set. So the cardinality of nothing is 0. Why are you laughing? Jamie, you seem to be enjoying this way more than you should. Right. What about unit? How many values in unit?
1.
Right? Unit. Unit has a value of unit. So cardinality is 1. What about Boolean? True and false. 2 values. So the cardinality of Boolean is 2. Right? So cardinality is pretty easy. Let's start talking about sum types, and let's study the cardinality of sum types. So sum type. I'm going to define this sum type, which I'm going to call plus, because plus sum, it helps. And a sum type can be either a left value, which contains an A, or a right value, which contains a B. So it's either an A or a B, right? And the reason I'm defining it like that is because this scala being a scala, we got syntactic sugar for absolutely everything to the point that it's widely confusing. But that allows us to write this like that, which I find quite nice. A plus nothing, or nothing plus B, which I find, at least for the purpose of this presentation, to be quite readable. So what is the cardinality of A plus B? Well, we have all of the A's wrapped inside of an A, of a left, and all of the B's right inside of a right? So the cardinality of A plus B is going to be the cardinality of A, because we have all of the A's, plus the cardinality of all of the B's. The cardinality of a sum type is a sum of the cardinality of the types. Sum, right? That's why it's called a sum type, just because you add the cardinalities. Now we're going to do a little bit of math here. Not anything too complicated, but we're going to do basic algebra. But before I do that, I'm going to have to introduce a scary word. I'm going to start talking about isomorphisms. Don't worry, I'm not going to talk about category theory because I just couldn't. We're going to say that two types are A and B are isomorphic when they have the same cardinality. And we're going to write it like that. So we're saying they're isomorphic because that means you have a one-to-one mapping from one type to the other. You just map, since they have the same number of values, you just map all the values from the one to one given value of the other, which allows you to go from one to the other without any loss of information. That's what an isomorphism is. We don't need any more than that. And having introduced that notion, in algebra, we can do cool stuff like 1 plus 1 equals 2, right? Well, that carries over to the types. This gives us unit plus unit is isomorphic to Boolean. And the transformation is very easy. For any type, for any value, you take a type that has the same cardinality. So 1, we take unit, 2, we take Boolean. Then you replace integer addition with type sum, and then equality with isomorphisms, right? And so just to show you that this actually works, let's look at how we map from one to the other. Unit plus unit has two values. We have either a left of unit or a right of unit. Boolean has two values, true or false, and there's your mapping, right? You can use one or the other. You don't lose any information. There are, for all intents and purposes, the same type. There are equal up to isomorphism, which is something I always like to say because it makes me sound so clever. We can, sums, algebraic sums have an interesting property, associativity, which tells us that no matter how, in which order we run this calculation, we get the same result, translates at the type level. And again, let's look at the mapping. A plus B plus C is one of left of A, right of left of B, or right of C. And A plus B plus C is a left of A, left or right of B, or a right of C. And there's your mapping, right? Again, we can clearly map from one to the other and back. And finally, commutativity. A plus B is equal to B plus A, which, as types, gives us the same information. A plus B is isomorphic to B plus A. And again, let's look at the mapping. A plus B is a left of A or a right of B. B plus A is a right of A or left of B, and we have an obvious mapping from one to the other, right? So this is one of the reasons we call them algebraic data types, is because we can do algebra with them like we used to from algebra in high school. So nothing too complicated. Now, oh yeah, and we have the neutral element, sorry. A plus 0 is always equal to A. And with some types, A plus nothing is isomorphic to A because, well, A plus nothing is a left of A, and it can't be a right of anything because we have nothing to stick into the right. And an A is an A, and we map left of A to A, and we're done, okay? Now, the next thing is product types. We're going to study the cardinality of product types with this type, multiplication of A and B, which is an A and a B, right? Quick extension method that I'm going to use to be able to declare values of type A and B. If I have an A, I can take the product of it with B to give me a product of A and B. Again, this is Scala. We can use binary type constructors in infix notations. So we get that, which again, I think is quite nice. Right. So what's the cardinality of an A times B? Well, that's what I'm doing here, isn't it? Right? This extension method allows me to write A times B and that's going to yield an A times B. So this slide is exactly about doing it to the values as well. Right, the cardinality of an A times B. Well, we have one A associated with all of the B's, and we keep doing that. And then we have the last A associated with all of the B's, right? So the cardinality of A times B is going to be the cardinality of A multiplied by the cardinality of B. The cardinality of a product type is a product of the cardinalities. Again, that's exactly where the name product types come from, because we multiply the cardinalities. And we're going to do the same thing we did before. We're going to do it a bit more quickly, because everybody's yawning quite a bit, so I guess I'm overstaying my welcome. A plus A equals 2.A, something fun to do. We can do that as types. And the only difference from before, we have added one new conversion rule, which is to say integral multiplication become product of types. So mapping is easy. A plus A is left of A or right of A. Boolean times A is false and A or true and A. And there's our mapping. Okay? And now we can do the same thing as we did before. Associativity works for product types as well. With an obvious mapping, A times B times C is A times B times C. A times, this is hard to say out loud, so because it's just, so you read it, right? And there's a clear mapping. I mean, the diagram is meant to show, to make the mapping obvious, so we have the mapping. And finally, we have commutativity again. A times B is equal to B times A, which works with types, because A times B is an A and a B. B times A is a B and an A, and we just map like that. We can go from one back to the other, and the two are isomorphic. And finally, the neutral element. A times 1 is always equal to 1. A times unit is always isomorphic to A, because A times unit is A and unit. A is A, and we can map from one to the other. Now, I have shown you how we study the cardinality of some types, product types. If you remember, the definition of an algebraic data type is a sum of products that might be recursive. So let's talk about recursive data types. List, for example. With the sum type, because this can be either a nil or a cons. And it's also recursive because cons is defined as an A and a tail, the tail being a list. So list is defined in terms of itself, right? We have list on both sides of the type assignment. So we're not going to be able to study the cardinality of list in that it's infinite by definition, right? And I don't want to go into infinity mathematics because that's just way too complicated. What we're going to start doing is I'm going to use this syntax to say we're going to study the cardinality of list of size 0. That subscript 0 means exactly that number of elements in the list. So list of size 0, that's just the cardinality of nil, isn't it? And nil has exactly one element, nil. If we keep doing, list of size 1. Well, that's going to be, as we've seen, the head and the tail. So that's going to be the cardinality of A times list of size 0, which we know the cardinality of the product is the product of the cardinalities, and we can keep simplifying by getting to this. List of size 2. Should be pretty obvious by now, same pattern. It's A plus, multiplied by list of size 1. So we simplify and we get A squared. And I'm not going to do the whole induction reasoning, but you know where this is going, right? The cardinality of list of size n is A to the n, right? So exponential types first, that's fun. We haven't talked about that before. Then let's talk about the cardinality of the list of a maximum size. So the superscript here means list of size at most n. And this is where things get a little bit weird, but a little bit fun, because that is going to be the sum of the cardinalities of the list of all the list of size I from 0 to n, right? Now we know how to handle the sum. We just get it out of the cardinality. We know what the cardinality of size list of I is. It's A to the I. And if you've done sum algebra, you should recognize that equation, which simplifies to this. And this is really weird, isn't it? We're doing division with types. We are doing division types. I don't think those exist, but we are doing divisions. And I'm not sure this is useful to know how to do that, but it's fun, at least to me. And if you don't believe that this works, let's take a quick example. Let's take list of size at most 2 of Booleans. Not too big an example, because otherwise it's never going to fit on the screen, but let's simplify it. We know that the cardinality of Boolean is 2, right? So that's 2 to the 3 minus 1 divided by 1. That's going to be 7. So we just computed that the number of possible values in a list of Boolean of size at most 2 is 7. Let's confirm. We have either a list of size 0, which is nil, or a list of size 1, which is true followed by nil, or false followed by nil, or a list of size 2, which is all that mess on the right. And if you count them, we have 7, exactly like we've computed, and that generalized to any type and any arity, which I'm not sure it's useful, but I find it very fun. Yeah, so count them, 7. So what we've learned, we have learned that ADTs have a deep connection to the algebra that you know, and that is why they're called algebraic data types. We have also learned that you can use this connection to prove fun facts about types. Didn't say useful, but just fun. And also, you can use that to pad talks and look clever. Yeah, I'm done. And in closing, just to make sure that if there's one thing, if there's one slide you remember from that entire talk, this is the one you should remember. ADTs make data structure simpler and safer. They make, so do generalized algebraic data types, GADTs, only more so. And if you think about data structures that way, that should have a lasting impact on the way you write code, and it's going to make your code better, safer, and easier to reason about, which I think was the promise I made in the introduction. So I've bookended this neatly, so I think we're about done. And if you have any question, now is a good time. Thank you. No question. Oh, good. Thank you. Whew.
I did mention like A to match the start
Yep.
C match the moving, so just have one type parameter on the case. Why it's
because so the case class itself has A, B, C, because you need to know the type, the before type of the first command, the after type of the first command, which also happens to be the before type of the second one, and then you need to know the after type of the second one. So you need 3 types. But you have 3 type parameters because you have 3 types to handle, but this extends the command of AC, right? So in the end, the type that exposed to the rest of the word is a command of AC, which only has 2 type parameters. But you still need to know the middle one in order to make sure that the 2 commands sort of commute.
But I expect it to be like case into moving whatever of leader, and before and after that the word that comes from the other side.
No, but that's just Scala-free syntax. So if you have one type parameter to one of your branches, then you have to declare all 3 and make them part of the signature. So what you're saying is technically correct in that, yes, we don't need the A and the C because you inherit them from the enum, but you still have to redeclare them.
Okay.
That's just Scala syntax. Yeah, it's a syntactic problem, but semantically what you're saying is correct.
Yeah, because it seems like it has five parameters now, because it's like...
No, actually, no. So enum are weird when it comes to polymorphism. If you have exactly the same type parameter as the enum, you don't need to declare them. But if you have any difference, then you have to redeclare all of them to remove any possible ambiguity. So you still only have 3 type parameters. It looks like there's 5 plus conflict because you have 2 A's and 2 C's and 2 B's. But really, you're redeclaring all the type parameters and overriding them. So really, semantically, what you're saying is correct. It's just Scala syntax is forcing us to make it a little bit more complex than the model you have in your head. You're quite welcome. Any other question?
Curious about the redundant case. Can you go deeper in, like how does the compiler?
The redundant, recursive.
It gives you an error when you manage redundant cases.
Right. So I'm not going to go back to the slides because you can't see that, but this is slide 442. If I have to go back to the middle of this, it's 200 click of the button, so they're going to take a while. But so the example I had was, you were saying we were working with a pretty printer for a moving command. So a command whose before parameter was moving. And if the compiler sees that in your pattern match, you're handling start, for example, whose before parameter is idle. if you're using generalized algebraic data types, the compiler has the capacity to compare types. So it's going to say, is idle and moving are idle and moving the same type? No, they're not. So this case cannot possibly happen. There is no scenario in which I'm given a command of idle and I have to match on a command of moving, because that can't happen. So the compiler is going to tell you, well, don't do that because it's impossible. There's no way this is going to happen. It's exactly like if you're writing a pattern match on Booleans and then did a case on a string. The compiler will tell you, well, these types don't match. You can't do that in this pattern match. It's exactly the same idea. Sorry, I'm just going to. Everybody all right with me turning this off? Because I apparently took quite a bit of time and we need the next speaker to be ready.